So hello everyone. I think it's the time to start of the next session. So I'm sorry. I think feel free to get a seat and listen to our presentation. And after that, I believe you can continue doing your a poster and discussion. Thank you. I'm sorry that our session is supposed to start. Okay. Yeah, feel free to take a seat and listen to the talks, and then later after the session you can continue your discussion. Sorry. Yeah, thanks. Okay, so our first presentation will be Chronos time-aware zero-shot identification of libraries from vulnerability reports. Will be presented by Le-Cong.
Hi everyone, I'm Thanh. I'm a PhD student from University of Melbourne, and today I'm glad to be here to present our work, Chronos, time-aware resource identification of library from vulnerability report. First, let's talk about the motivation of this work. Recent years, we observed the increasing usage of third-party library on software development. Therefore, to secure software, now maintainer and developer not only need to monitor vulnerability in their own source code, but also need to aware about the vulnerability in the third-party library that might affect the reliability of the system. National Vulnerability Report database curates the vulnerability report which contain the detailed vulnerability occurring in third-party library. This report, however, is not exhaustive and cannot list all the affected library. Therefore, the human effort required to identify the library related to the vulnerability. This effort, however, resource and time incentive because the huge number of possible labels. So, motivated from this situation, we believe that automated approach for identify affected library is necessary. And then having automated approach, we can reduce significantly the human effort. Now let's formally describe the problem. First, we have a vulnerability report which contains a lot of information, including the reference. And then we build an AI model to automatically identify affected library. And then in the expected output, we want to have a list of affected library from this report. To address this problem, private work proposed to use XML multi-label classification and utilize FastXML to address this problem. Then the next work tried to use deep learning for this problem. And the result is quite promising. But problem here is we found that this work rely on the assumption that the library in the training data is same as the library in the inference data. So they use random splitting to collect the training, testing, and validation data set, and they don't aware about the time, established time of the vulnerability report. And we found that this is not suitable assumption because set of affected library could evolve over the time. Then we propose a time-aware evaluation. We use historical data for the training and use future data for testing. And interestingly, we found that the performance of state-of-the-art significantly dropped from the 0.7 to 0.25. And we found that the problem comes from the involvement of the label. For example, we can see that in our experiment, we saw that more than a half of the library in affected library is new and unseen in training data. That means the performance of the supervised learning is at most 50%. Therefore, we propose Chronos, a practical library identification approach based on real-shot learning. Sitting at the core of Chronos is a real-shot learning component. In this model, we use XML, the state-of-the-art of real-shot learning for XML problem. And then we use the TF-IDF for extract the feature of the description and the label. Then XML will model relevant between the description and label by analyzing their linear feature interaction. Then we can see the formula here. Then we further improve the performance of the real-world learning component by using some domain-specific and task-specific mechanism based on the two observations. In the first observation, we observe that additional document referenced in the MVD entry, such as the bug report mailing list, can help to distinguish multiple previously unseen labels from another. And second, we observe that exploiting the temporal connection between vulnerability report and affected library can help to boost the precision accuracy. Particularly in the data enhancement, we do two steps. First, we collecting the reference data, and second, we enhance the library feature by subword splitting. Particularly for the first one, in the vulnerability report, we have a list of website reference. So we build some crawler to crawl the textual information of the website. And then, because we have too many website reference, we find a set of 12 domains that cover most of vulnerability report. Then we build some, manually build some web crawler for this. And finally, we also apply some pre-processing to ensure the quality of the data. For library subword splitting, the motivation is that we want to enrich the feature that helps to determine the label associated with the vulnerability report. So we apply the state-of-the-art token splitter to split the token into sub-token, like we can see some example here. Then, finally, we observe that the vulnerability in the same time range are more likely to affect the recent version of library. So Chronos uses a strategy to prioritize the version of library that have been recently affected by vulnerability. So we propose a time-aware assessment. Then we'll see time-aware assessment use a version store to track the different version of each library and use a cache to store the recently affected library using least recently replacement policy. And then based on these version store and cache replace, we perform the time-aware assessment in two steps. In the first one, we replace replacement with favor newer library and update at a recency bias for the time constraint. So I don't present it in detail, but if you're interested in, you can see in the paper. And in terms of evaluation, we compare the performance of Chronos with the state-of-the-art, including supervised learning, traditional information retrieval, and some handcrafted heuristic. And we can see that Chronos significantly outperformed the baseline. And the improvement of performance comes from two components. For real-world learning that perform better than supervised learning, and data enhancement and time-aware assessment, which can further improve the performance of ZXML. In conclusion, in this work, we highlight the involvement of affected library in the problem of identifying library from vulnerability report. And then we empirically investigate the state of that on a new setting, and showing that the significant drop on the performance of state-of-the-art. Then, to address the problem, we propose Chronos, a practical library identification approach based on real-world learning and domain-specific mechanism, data enhancement, and time-aware assessment to further improve. And our experimental results show that both real-world learning and domain-specific mechanism yield a substantial improvement, resulting in Chronos outperforming state-of-the-art approach. Thank you for listening. This is my presentation. Any question as welcome.
Hello, thanks for your presentation. And I have a question about those library matching processes. You use the machine learning techniques to match different candidates with their libraries. So for some platform like the PyPy and NPM, I think, why don't you directly use the CPE? I think their package name are their CPE.
Thank you for the question. We also, in private work, some industrial partner also try to use the CPE configuration, but their results show that CPE configuration only cover, I don't remember correctly, 30% of the affected library. So that means it's not exhaustive.
The 30% means all the platform or for specific platform like PyPy in Python?
Actually, in current work, we use NVD, National Vulnerability Database.
NVD, I know NVD is a vulnerability database, but I mean for those libraries, you have different libraries, like the Java libraries are usually published in Maven, right? And Python in PyPy. Yeah.
Currently, we do not use, in our dataset, do not contain the PyPy and Maven.
You do not contain PyPy and Maven?
Yeah.
Then what kind of language are you aims for?
Actually, we use all the vulnerability report in the CVE, but we I'm not sure. Can you repeat the question? Why we use a Maven and what?
Because by my understanding, you use all the NVD CVEs, and that's a mix of the different languages, right?
Yeah.
Yeah, including the Java package, the Python package.
Yes.
And yeah, I mean, they have different unique features for their library. Like for the PyPy, their package name is their library name.
Yes.
And for the Maven, they may have sub-level name, like the Maven sub-module. Like,
I see. Yeah. Currently, we use the name. Actually, I use the dataset from the private work. So I actually use the label from the private work.
Okay.
Yeah.
Another question is how will you use this library? Like you have this matching, because yesterday I listened the David Liu's presentation. You aims to build a vulnerability library database, and right. Yeah. Do you have any plan how to use this database?
Actually, I think this paper is a part of the project, and in this project we have an industry partner in Veracode and Huawei, and actually they are trying to build the database. And I think that last week I received some email from the Huawei. They say that they try to incorporate into that platform soon, but I'm not the internal guy, so I'm not the correct plan.
Yeah. Thank you very much.
Yeah, so GitHub's Dependabot will look at a project and know all of the dependencies, and it knows through the NVD what all the vulnerabilities are in all of your dependencies. As far as I know, it doesn't need any kind of AI or classification. So what are the situations that your approach catches that Dependabot doesn't?
Thanks for the question. First talk like first of all, why we have a multiple affected library here. Like, for example, we have vulnerability in the library, but maybe multiple versions of this library can include this vulnerability. So it should be multi-label. It's not like client project. It can actually library. And in some other case, we have some project which implement use some language. The vulnerability comes from this language, but after that, because this library mainly use the language, so we have a different security researcher, so they report different affected library. But actually, both of them is true, because the library mainly use this language, so it should be a vulnerability of this library. But also, it's the vulnerability of the language, so we have a multi-label here. It's not like a client project. It's like the multiple version and multiple library which is contain this vulnerability. Yeah. If you want to see some example, I can show you after the session. Yeah. Yeah. Thank you very much.
Okay. Good day, everyone. Today is my great honor here to give this talk about cross-project vulnerabilities in the Maven ecosystem. This is joint work of my colleague Yu and my supervisor Ming from Huazhong University of Science and Technology. Okay, let's start. Nowadays, open source libraries becomes a key ingredient of the software development. According to a report by SNCC, a single software of the main programming language needs at least 20 dependencies to build with. Along with convenience, it also brings many high security risks. For example, the famous Log4j core remote execution vulnerabilities So it's no surprise that this vulnerable dependencies ranks as high as 6 on the OWASP top 10 list. So to mitigate this problem, companies apply SCA, which is the software composition analysis tool, to scan and extract the dependencies from the user's input and compare them with the vulnerability database. And it will issue a lot once found any vulnerabilities match in their database. But the problem with this approach is that even though some users claim they rely on certain vulnerable libraries, they may not actually be affected by it, thus causing numerous false positive and false trading alerts. Oh, sorry. Let's take this vulnerability, for example. This is a past traversal vulnerability lies in the Apache Commons IO, and it's caused by insufficient input check. And here is its vulnerable version. And sorry. And the quickest way to fix this problem is to upgrade to above 2.7. But whether upgrading is the best option for all the downstream of this library, since considering the upgrade may have high cost like capability issues or lost some certain features. So we take a detailed look of its downstream, like here, the GitHub API. It actually uses one of the API of the vulnerable library, but it won't lead to the vulnerable function, so it does posing no security risk to the downstream. While for other downstream, like here, the Open Hub core and the PMD core, they have passes to the vulnerable functions, while they're different in terms of the functions involved in this pass and in this passes and the context around the invocation. So whether both of them need an upgrade or one of them or neither of them is unclear. And we also further noticed that different downstream users take different response to the vulnerabilities. Like here, the Open Hub core take an upgrade as a response to the vulnerability, while in the same situation, the PMD core take no actions at all. So all these observations sparks our interest in finding more information about the cross-project vulnerabilities especially in this Java language, and especially in its package manager Maven ecosystem. Specifically from this accept, we want to know more information about this accept to help developers like us know more about this cross-project vulnerabilities. Now let's dive into our empirical study and find the answer to these questions. We first start with our data collection part. To create a large-scale data set, we collect data like vulnerability and their patches from different sources. And we get this amount of vulnerabilities and patches. And because we have to perform reachability analysis, so we should have a destination like the vulnerable function. So we perform the vulnerable function localization. And then we do the GAV identification to map the vulnerability to the certain component in the Maven ecosystem. And then, because our work focused on the cross-project vulnerability, we need to identify the downstream project affected by the vulnerability upstream. So we use Eclipse Azure to construct the Maven dependency graph and identify the downstream that were using the vulnerable upstreams. So we have this triplet here. At the end, we obtain this dataset consisting this amount of CV and the triplets. Because of the time limit, we leave many details behind. They can be found in our paper, and any questions about that are welcome. And to start with our first RQ, which is about reachability, we analyze reachability to the vulnerable functions through direct calls and transitive calls. We use this concept to illustrate the result from different perspectives. To build the call graph and control flow graph, we use Suit, a famous Java static analysis tool. And for the first result is we find the regarding to reachability of the vulnerable function, we found that 80% of them were not reachable at all. And for those that were reachable, transitive calls are most common, whereas private functions can also be assessed as well. And to measure the impact of vulnerabilities to measure the extent of the vulnerabilities impact, we calculate the ratio of the downstream project that can reach the vulnerable functions. On average, vulnerable upstream threads 10% of its downstream projects. And we also observed interesting correlations between this value and the reachability of its commonly used API of the upstream, which means if the commonly used API of this vulnerable upstream is reachable to the vulnerable function, it will lead substantial of its downstream to be affected. This highlights the need for the SA companies and upstream developers to pay more attention to this kind of APIs in the vulnerable libraries. And second, we investigate the reachable passive details to approximate the explorability of this vulnerable function. And we know that ICFG passes may encounter different input contexts and conditions. Like some ICFG may require certain conditions to met, while some downstream invocations can, while some other invocations can finally reach the vulnerable functions without regard to the constraint alone. Like here, the ICFG ratio, reachable ratio is 1, which means all these ICFG passes lead to the vulnerable functions, making these vulnerable functions more accessible. And considering the context of the downstream invocation, there are 3 kind of situations. It can be guarded by a checker or be propagated as a parameter to other functions or be returned. And we will investigate the reachable passes from these above perspectives. And as a direct indicator of reachability and difficulty, we first count the length of the reachable passes. Nearly half of them the length is less than 5. And for the ICFG pass ratio, we found around 20% of the ICFG passes has a reachable ratio of 1, which means all these passes can lead to the vulnerable functions without regard to the constraint along the way. And as I just mentioned, there are 3 contexts of the risky invocation in the downstream. So there are 8 combinations of them, and here is their distribution. We found that around half of the risky invocation have no triggers, and 30% of them, the input of them, will further propagate, which may cause further security issues like some data leakage. And now, after we analyze code and software, we are now analyze the human about their behavior. And we examine data downstream user behavior. We select some active downstream. We represent the overview of this data visually. Here is a case. Here is a case. With the black line here means the publication date of the vulnerability, and the yellow line here means that the downstream is using this vulnerable libraries. And here is the aggregate value of these cases. So we can, it's clear to see that color is much lighter after the black line, which means the majority of the downstream project take actions such as remove the vulnerable libraries after publication of the CVE. But we can still see some of them take no actions and still relying on these vulnerable libraries. We first analyzed the different response. We found 80% of downstream will take actions such as upgrading or even downgrading. Then we analyzed the response time. We observed that the downstream users who were reachable to the vulnerable functions respond more quickly, and especially for those directly called here. And after all this, we found that the reason behind the response is still a mystery. So we conduct a user survey among the downstream developers to understand the reason behind their response to the vulnerabilities. As for how they noticed the vulnerability, we found that even though with many false positives, SCA tools were still the primary way for the most developers to detect the vulnerabilities. As for why they take the action, most users, they respond due to the security issues. Some also upgrade for other reasons, such as routine upgrades, and fix the problem by the way. And to determine whether they were affected, most developers manually checked whether they are affected, and this requires a significant domain knowledge. And after all these findings, we have some recommendations for different stakeholders in the Maven ecosystem. For downstream developers, we suggest conducting further analysis, such as reachability analysis, to before taking any actions such as unnecessary upgrading. This is because we found the majority of the upstream wormhole functions are not reachable. And for upstream developers, we recommend better managing and check the contain vulnerabilities and provide more detailed information to downstream, which will facilitate more precise analysis. And for future researchers, we suggest developing a precise model to assess the threats of the upstream vulnerabilities. And our findings in RQ2 can give guidance to construct such a model. And in summary, we collect a large-scale data set of the cross-project vulnerabilities in the Maven ecosystem and conduct an empirical study and a user survey to understand their threats. We distill a series of findings and suggestions for developers in the software ecosystem. And in the end, we agree with Bruce that security is not a product, but a process. Ensuring software ecosystem security is a never-ending journey that requires the collective efforts of all the developers. And here is my presentation, a simple and relaxing empirical study. I hope you guys enjoy it. Thanks very much for attending.
Hey, thanks for the interesting talk. Did you analyze the impact of semantic versioning? So, for example, I could imagine that if it's just a patch or minor update, then developers are much more likely to move to the next version of a dependency than if it's a major update.
You mean some downstream only try to do some routine upgrade, but they are not upgrade for the security issue. You mean that?
No, what I mean is it may be more likely that the downstream package updates if the version number is only bumped up at the end, basically. So if it's just a patch update and not a major update.
Oh yes. You mean when I analyze the downstream behaviors, whether I choose the minor upgrade or the major upgrade?
I think my question is if the kind of upgrade of the upstream library impacts the likelihood that the downstream package moves to the newer version.
Actually, I haven't got your question. Maybe we can discuss offline.
Okay, yeah, let's take it offline.
Sorry.
Yeah, thank you for the work. So reachability analysis is really hard to do in languages that aren't Java. And on your first slide, you had a pie chart that had a whole bunch of languages like languages like JavaScript, reachability, call graphs. That's really hard to do in languages like that. And then on top of that, reachability is really hard to do when there's multiple programming languages involved, right? What do you do then? Like, is there another solution to this issue beyond reachability? I'm curious.
Oh, thank you. Actually, the target of the analyzed target we analyze is pure Java program, so it's not a cross language problem. So, and for what you said is right. The reachability analysis in Java is very not a very easy did, because you have to deal with some reflections and other problems, dynamic features in the Java. We tried our best to mitigate this problem by using the certain framework with point analysis to, but it's hard to consider all the factors like the dynamic features. It's not scalable in our experiments, for we consider so many downstream and upstreams. Thanks. Thank you.
Thank you very much, everyone, for joining the presentation. Today, I'll talk about SegWit.js and executable server-side JavaScript benchmark. This is a joint work with researchers from CISPA, MIT, University of Stuttgart, and IIT Kanchipura. I will describe how we developed the suite, and we'll try to convince you to use our suite for your next security evaluation. Now, those of us working with JavaScript know how difficult it is to tackle the security challenges. And that's partly because of the ubiquitous nature of JavaScript, but also our tendency to use trivial packages, for example, like is-odd. And that's why over the years, the number of JavaScript NPM packages has increased exponentially. But if you look at the number of NPM vulnerability report, although it's increasing, doesn't actually match the growth of the number of packages, which indicates there has been a lot of opportunity to work of research in this area. Now, even though there has been a lot of great work has been published in this area, for example, work on prototype pollution, work on DDoS, code injection, and very recently supply chain attacks have been published in the top security and software engineering venues. There has been one thing was missing. There is no security-oriented benchmark for Node.js, which makes it difficult to evaluate, compare all these great works as they has been tested on different set of programs. As a result, it slows down the research, waste times, as everyone has to curate their own set of programs for their own research. To bridge this gap, we decided to develop SecBench, but the question is now, how does an ideal benchmark should look like? We believe it should have 4 properties. The first one is the benchmark should be realistic. That means it should include a diverse set of real-world code without any modification. The benchmark should be executable so that we can use it for runtime analysis. And the benchmark should be two-sided. That means if available, the benchmark should include both vulnerable and fixed versions, which will enable us to use it for to compare different detection and mitigation technique. And lastly, the benchmark should be manually vetted and cross-checked to confirm the vulnerability and metadata. Now, before I'm going to show you how does our SecBench achieve all these 4 criteria, let me show you how we developed the suite. We started by collecting vulnerability report from 3 different sources: Snyk, GitHub Advisory, and Hunter.dev. The next step is filtering the candidate. There are more than 5,000 vulnerability reports for JavaScript on this on the security database. As I mentioned, this is a server-side JavaScript benchmark, so we did not include any client-side exploit, for example, like cross-site scripting. Our first criteria is we only focus on vulnerability. That means we do not include any malicious packages. We also do not include any packages. That is, for that we cannot present any executable exploit. And lastly, we do not include any vulnerability or packages that cannot be installed in our system. That is not reproducible. Also, is not compatible with our setup. After the filtering process, we included in total 600 exploits in our benchmark from 5 different classes. Prototype pollution and path traverse are the 2 largest classes with 192, 169 exploits. The next step is creating the proof of concept, POC. Now, if the public vulnerability report contains a POC, we adapt it and include in our benchmark. But if there is no POC available, we create the POC ourselves, utilizing the natural language description of this of the exploit, which is available in the vulnerability report. We implemented this benchmark as a set of unit tests in Jest, which is the most popular testing library for JavaScript. This is a test case, Jest test case for prototype pollution in Lodash. This is a payload which we pass to the Lodash library to trigger this exploit. Now, before triggering this exploit, we need to check if the target property is not already defined. For example, in this case, the target property polluted should be undefined before the exploit happened. The second is the next step is we call the vulnerable function of the library. For example, in this case, the margf, and we pass this payload to that library and run the test. And lastly, we check with the security oracle to make sure this exploit is successfully executed. In this case, for example, the key value of this key polluted should be yes if this exploit is successful. It's only possible, and it's only possible if this exploit is successful, the value will be yes. Now, going back to the property of an ideal benchmark, let me show you how we achieve four criteria. First of all, our benchmark is realistic. It includes 600 NPM packages without any modification. All the exploits in our benchmark is executable. It also includes a security oracle to make sure that each exploit is successfully executed. Now, thirdly, our benchmark is two-sided. 48% of the exploit in our suite include both vulnerable and fixed version, and for the rest, there is no fix available. And lastly, our benchmark, each entry of our benchmark is manually tested and cross-checked by 3 different researchers. But now you can ask, okay, you developed a great benchmark, but why should we care? Now let me show you 2 use cases of our benchmark to demonstrate how our benchmark can be useful for your next security evaluation. But keep in mind, this is just 2 examples. We have more use cases in the paper and more details. Please check our paper for more details. The first use case is finding a mislevel vulnerable version. Oftentimes, we found out that in the security database, the vulnerable version information for a package is not always right. So the question is then, how do you determine if a particular version of a library is indeed vulnerable to a particular exploit? And this is where our benchmark can come to the rescue. Let me show you how this particular problem can be solved using our benchmark. Let's start with a library. We want to test and install the desired version. Then we can use the already available JS test with this version and run the test. Now, if the test is successful, we can say this library is definitely vulnerable to this exploit. And then we can check with the security database, for example, Sneak, and match this information to check if this information matches. But if this test fail, unfortunately, we cannot say for sure this version is safe. And that is because for few packages, for the legacy versions, the test might fail because of the compatibility issue. Now, if you want to do this for all the packages or for all the version, we can just repeat this process, and we can do it using our provided script in the benchmark. This figure shows a few results of our experiment. The red box shows the vulnerable versions, and the gray box shows the non-vulnerable versions. Now, we found out in total 168 mislevel versions from 19 packages. Out of them, 2 are JSPDF and Shrivel are zero-day vulnerability. That means the latest version of this library are found vulnerable, even though they were labeled secure in the database. And for cases like this, where we found the package safe, but it was labeled vulnerable in the database, we cannot say anything for sure, as I explained previously. So we did not report any number for this type of cases. And the second use case is finding flawed fixes in the code. Now, oftentimes the developer deployed a fix for a security vulnerability which doesn't cover all the corner cases. But the question is then, how do you find this type of flawed fixes automatically at a scale? Let me show you how we can do this. Let's start with the library you want to test, and then install the desired version. And then we can use the payload we want to test against this library, and use this payload with our JS test, which is already available in the benchmark, and then run the test as previous. As previously, if the test pass, we can say for sure this version of this library is indeed vulnerable to this payload. But if the test fail, we cannot say for sure this version is safe, as I previously explained. And if you want to do this for all the versions or all the library or for all the payload, we can just repeat this process, and you can do it very easily using our provided script in the benchmark. Now, we use this experiment to find the 3 mutation of this key proto, and we found out 18 zero-day vulnerability, and we report them to the developer and the Sneak, and we were assigned 12 CVE for our findings. So, in summary, although there has been a lot of great works in the JavaScript, there was no security benchmark. That's why we decided to develop Segbench, which is realistic, executable, two-sided, and weighted benchmark. And one use case of our benchmark is finding mislevel vulnerable versions. And the next use case is finding flawed fixes in the code. There are more use cases available, as I mentioned previously. Please check our paper for the details. And lastly, our benchmark is already publicly available in GitHub. Thank you very much for your attention. Please feel free to ask any questions.
Thanks for your great presentation. I'm Anna and from the Technical University in Darmstadt, and I also built a benchmark and worked on JavaScript several years, I think now ago. And I think it's a good work you did. What was one of your key insights with the guidelines you set to building an app, like reviewing with 3 researchers? Would you do it the same way, or how would you adapt the process?
So the way we worked is the one researcher first gathered the POC or write the POC, but also helped from the other researchers. And then second researchers manually go through all the POC to test them that, okay, these POCs work. And the third researcher cross-check them actually to say that, okay, these 2 processes were correct.
Thanks a lot for clarification. That makes a lot of sense, I think.
Thank you very much.
Okay, I have a question. So for the mutation, what kind of operators you're using?
So, sorry, can you repeat what do you mean by operator?
You just, in the last one,
yeah.
you just do a mutation. So what kind of mutation operators?
So in our case, the mutation is created manually actually. For example, we muted the keyword proto actually, and we've kind of manually created this mutation. But if you can do it also automatically, but there is a different process you have to use actually. But in our case, we manually found this mutation.
Okay, got it.
Thank you very much.
Thanks. Yeah. Okay. So if there's no more questions, we're going to go to the next presentation. Thanks to the presenter again. Yeah, for the presentation. Yeah, the next presentation will be on privacy weaknesses and vulnerabilities in software systems. By Patrapon Thingership.
Yeah, Patrapon. Okay, so good afternoon, everyone. My name is Patrapon. I'm a PhD student at the University of Wollongong. Today, I'm pleased to share with you about our work entitled on privacy weaknesses and vulnerabilities in software systems. I've been working with Professor Huadam and Professor Adityagus on this paper. So in this presentation, I'm going to discuss on the motivation of our work, approach we used, limitation and opportunities to continue this work. Let's get into detail. So we have seen many news about personal data breaches across the world. Some of you might have already been victims in the personal data breaches. We have received so many scam calls here in Australia. Recently in Thailand, there was a big news about personal data breach. The hacker threatened to publish 50 million records of personal data of Thai citizens, which is almost 70% of the world population in Thailand. This is quite big, right? These kind of incidents poses a serious privacy threat to individuals. Security and privacy are sometimes discussed together, but they are not the same. Privacy focuses more on personal data, data subject rights, how personal data is processed, and about data protection compliance. While security emphasizes on protecting data and systems from attackers, ensuring confidentiality, integrity, and availability of the data, and how to apply security mechanisms and controls in the systems. Therefore, this motivates us to investigate more on privacy in software systems. Common weakness enumeration, or CWE, contains a list of weakness types found when developing software. It explains the weakness in detail and provides some examples to illustrate that weakness. On the screen, I'm showing you one of the CWEs. This weakness describes the exposure of private personal information to an unauthorized actor. You can see that the privacy is hidden inside this security weakness, as it involves personal data. Although the developers research for security and privacy-related weaknesses and vulnerabilities in the CWE and CVE, it's not clear to what extent privacy concerns are covered in those systems and whether privacy receives adequate attention it deserves. To investigate into this, we first developed an approach to identify privacy-related vulnerabilities in the CWE and CVE systems. First step, we obtained all CWE and CVE records from their websites. Those are the number of the records at the time of when we collect the data. After obtaining the CWE and CVE, we perform keyword searches to filter out the records that do not have privacy-related keywords. A set of keywords consisted of 37 terms categorized into 4 groups as shown in this table. We found that 185 CWE and 1,088 CVE records that contains at least one of the specified keywords. Next, we manually examine each of those records to identify privacy-related vulnerabilities. We will consider it is a privacy-related vulnerabilities. Either it involves with any processing of personal data or the vulnerabilities that leads to the violations of individual rights. So we went through all the shortlisted CWE and CVE from the previous step to determine the vulnerabilities that meet these criteria. Finally, we got 41 and 157 privacy-related CWE and CVE respectively. You can see that the coverage of the privacy-related vulnerabilities in both systems is quite limited. So we then investigated how those privacy-related vulnerabilities identified in the CWE and CVE system address common privacy threats in software applications. To do this, we conducted an explanatory study on the literature of the privacy engineering research, privacy regulations and frameworks, and additional sources. For the privacy engineering research, we perform a systematic literature review to identify privacy threats in software engineering publications that were published from 2001 to 2020 in 17 highly recognized software engineering publication venues. We first acquired 1,434 papers from the search. But after applying the inclusion and exclusion criteria, there were 417 papers left in our study. For the privacy regulations and framework, we have studied 7 well-known data protection regulations and privacy frameworks such as GDPR and HIPAA. We identified the privacy threats related to the right of individuals on their personal data processing from these materials. Lastly, we also investigated the privacy threats included in several reputable organizations such as OWASP and Norton. These sources cover the recent trends of privacy risk and attacks. So after identifying the privacy threats in the explanatory study, we have built a taxonomy of common privacy threats upon the taxonomy developed by Stallings. We tailored this taxonomy and refined it into a more concrete version that addresses privacy threats in software engineering. The taxonomy consists of 4 categories of privacy threats, which are information collection, information processing, information dissemination, and invasions. The yellow boxes in the figure represent the categories and subcategories included in the original taxonomy. Those blue boxes are the privacy vulnerabilities we have identified in our explanatory study. We map the privacy-related vulnerabilities identified in the CWE and CVE in the first step to these privacy threats identified in this taxonomy. After these processes, we found that only 13 out of 24 common privacy vulnerabilities were covered by CWE and CVE. The boxes with red outline are the privacy threats that are not covered in the current system, the CWE and CVE. The green box represents the common privacy compliance in software application. The privacy threats in this group have not been addressed in the original taxonomy, so we proposed the compliance group as an extension to the original taxonomy. To fill the gap we discussed in the previous step, our study proposed 11 new common privacy weaknesses. We chose to propose these weaknesses as CWE instead of CVE because CWE is more generic and similar to our taxonomy of privacy threats. So we follow the CWE schema to define the new CWE entries, which include attributes such as name, description, mode of introduction, common consequence, detection method, potential mitigation, and demonstrative example. We provide a demonstrative example of the new weaknesses by extracting the code fragments, issue reports, and commits from the real software repositories hosted on GitHub. So I'm now showing you one of the example of new common privacy weaknesses that we proposed. These weaknesses is about not allowing users to withdraw their consent. We describe the weaknesses following the CWE schema as shown in your left-hand side, and the code snippet is shown on your right-hand side. We are aware that there are several limitations to our work. Firstly, the keywords might not result in the complete list. And secondly, there might be other sources of other privacy threats that we have not identified. However, we have applied several strategies to mitigate those limitations. For keywords, we use the frequent terms and general terms to make sure that we cover privacy-related CWE and CVE as many as possible. We also defined a set of inclusion and exclusion criteria to select the relevant papers. So our future work would include the extension of our explanatory study to increase the generalizability of our taxonomy and to develop new techniques and tools for automatically detecting privacy vulnerabilities in software and suggesting fixes. And that's the entire journey for our paper. Thank you for your attention.
Hi, my name is Big Pathanamon from the University of Melbourne. Very nice work, very nice talk. I just have very simple questions about the keyword list that you craft.
Yeah.
Can you elaborate more? How do you do that? And where? I'm not sure you have mentioned about frequency of the term and where do you get the data from? Yeah.
Okay, so our keywords are, we define that when we calculate the frequency of the terms that we found. For the first group, it is the general terms related to weaknesses and vulnerabilities in privacy. And for the second group, it is the keywords that normally refer to the personal data or personally identifiable data. And the third group, it is the keywords that related to privacy and data protection regulation standard and framework. And the fourth group is the keyword that are frequently seen in the privacy policies and literature. Thank you. Any other questions?
Well, I have a question about the relationship between privacy and the vulnerabilities.
Yeah.
So in many cases, like we have I don't know maybe it's correct or not, but like a pre-assumption that privacy and vulnerabilities are closely related.
Yeah.
But in many cases, they are kind of independent from each other. Basically means that when a vulnerability is triggered, exploited, whether it is a privacy issue is depending on what kind of data is being what is the scenario of it has been triggered.
Yeah, so it's like when the personal data is stolen or it's hacked from the system, we consider that is a privacy vulnerabilities.
So in your case, it's more of like whether the vulnerability can be exploited for privacy purposes, but it does not necessarily to be exploited for privacy purposes, or it's like a more as a closer relationship that whenever this vulnerability is exploited, it's very likely it's going to be a privacy related issue. So there can be a possibility and there can be a correlation.
Yeah.
So what kind of findings do you think is more on the possibility side or is it more on the correlation side?
It is a possibility side.
Okay, I see.
Yeah.
So it's more like the vulnerability can be exploited with like privacy purposes, for example, which resulting in a privacy leak, but it does not necessarily cause privacy.
That's right.
Thanks for clarification. Okay, so any more questions? If there's no more questions, we're going to call for the next presentation.
Thank you so much.
Yeah. So our next presentation will be a 2 demo from CSIRO Data 61, Zhao Sun.
Hello everyone, I'm Zhao Sun from Data 610, and today my presentation is a multifaceted vulnerability searching website driven by a spec-level vulnerability knowledge graph. And and due to convenience and cheap, many open source software are widely used in the commercial level product, and at the same time, the vulnerabilities are widely spread and hard to be detected. So to solve it, lots of organizations build their own vulnerability database, like the NVD, which is one of the most popular vulnerability database, and the IBM built by the commercial company, the OpenWorld Mellis built by the different people, and the exploit database built by the white hackers. And one problem of those databases is information discrepancy because they have different regulars. Like shown on the corner for the same NVD or same CVE, they use different information, like the different granularity of the things to describe the same vulnerability. So sometimes it can cause confusion, and sometimes it contains error, like the different version records. And so to solve this problem, we extract the vulnerability key aspects from the vulnerability descriptions of each dataset. Which includes the product, version of vulnerable product, vulnerability type, vulnerable component, root cause, attack vectors, and the impact. They are defined by the experts, and they are recorded in the meter CVE template. And we collect them together and use the machine learning model to extract them and build the knowledge graph. And here we select 4 databases, including NVD, IBM, Exploit, and OpenWorld Mellis. And we use the BERT-based name entity recognition and the question answering model to extract all the aspects. And the initial training data is manually labeled. And we built this knowledge graph, and it contains lots of information like the origin of the database and the CVSS items. There are also discrepancies among databases, like the impact denial of service is similar to the crash. So we use the k-means clustering to cluster the different concepts together and manually resolve them, so to try to relieve the discrepancy issues. And we built, based on knowledge graph, we built this website. And if you like, you can access the link to access this website. And at the top is a searching panel. You can use the CVE ID or any vulnerability key aspect to search the things you're interested in. Like, well, I'm interested in the Intel, or I'm interested in the buffer overflow. Then we can specifically filter out the vulnerabilities about those features or key aspects. And at the side, there is a multifaceted filter panels. You can use them. For example, I'm interested in Windows. There are still lots of products like the Windows XP, Windows 10. Then you can use specific vulnerability key aspects to filter them. And the searching is achieved by this formula here, by the similarity of the words and similarity of the phrase and the synonyms. Yeah. And we also have this comparison table, and based on this table, we can compare the different information from different original sources, so it can give the user a direct view about the discrepancies across different databases. And based on the knowledge graph, we also have this word cloud statistics, like for the specific product, what is the most frequent version of it? and in the history, what is the most frequent vulnerability type aligned with this product. And by this way, user can have more clear about specific product or specific vulnerability types. And this function is unique compared to the other existing vulnerability database. And for the evaluation, we're going to evaluate the quality of the vulnerability key aspect extracted by the machine learning, and want to use the sampling method to validate the quality of those clustering things. And for usefulness, we try to we want to conduct user study between two groups of participants. We can let one group of participants use our demo, and others use the search engine, and ask them to conduct a report, compare the safety of similar products like the Intel versus AMD processors. And we will record the richness, correctness, traceability, consistency, efficiency to comment their performance. And I think with our multifaceted knowledge graph, the participants are supposed to find vulnerability features quickly and thoroughly. And that's all my presentation. Thanks very much.
Thank you very much for the presentation. It's a great work. Does the when you show the product actually, does it include only the like the hardware actually, or does it include the software?
It includes all these things like the hardware and software, because it's extracted from the CVE description, like the NVD database. And actually, we use the CVE as their product name. CPE as their product name. Yeah.
Oh, thank you very much.
A very quick question. Is this data set kind of like being automatically synchronized with the existing NVD, or that they have the database?
Currently not. It's because it's very complex in the middle processes, so we only have to up to the 2020 the data.
Okay, so it's like a staged version.
Staged version, okay. Yes, that's just a demo. But use the same processes, we can do update. Yeah,
sure. Thanks.
Yeah. Thank you.
Okay. So. If there's no more questions, we go to the next presentation.
Hello, everyone. Thank you for being here for my presentation about the study of Java deserialization vulnerabilities. My name is Iman Sayar, and our paper was accepted and published in ACM TOSEM 2023. So this work was done with collaboration with Professor Alexandre Bartel, Eric Boden, and Yves Le Traon, in the context of my postdoc at University of Luxembourg. So as you may understand, my presentation is about deserialization and serialization vulnerabilities. So before starting the content of our, let's say, contributions, I would like to show to you what is serialization and deserialization. So serialization is the process of transforming an object into a sequence of bytes. So for example, here you have a class, Java class, which implements serializable interface in order to use the serialization mechanism. And when you instantiate this class, you will obtain an object of this class. And the serialization will allow us to obtain a sequence of bytes, which is unreadable by human. So this deserialization is the inverse process. In other words, it allows to reconstruct or to build the object starting from this sequence of bytes. So deserialization is so effective and is useful for memory management. However, it is very dangerous when attackers may provide or insert data that are malicious and that they will lead to deserialization attacks. So the most known attacks are remote code execution. So in our paper, we did two big analyses. The first analysis is about 19 public exploits by doing automatic experiments. We did more than 256,000 experiments. And the second one is about the study of 104 CVEs of real-world applications that are vulnerable to deserialization attacks. And to do that, so we were using the Java language and Java applications, and we were using a YSO-serial tool, which is a free tool providing a proof of concept about 34 deserialization attacks. The first step of our analysis consists on reproducing, first of all, these attacks using this tool, YSO-serial. So here I show to you the call stack of an attack, which concerns the update 21 of the GTK 7, in which we start from the call of read object in my main class, and then going through the calls, the successive calls, we obtain the attack, which is the runtime exec. So here the code of the attack is just launching the execution of a code, remote code execution. And so what we did is that we identify what we call gadgets. So a gadget is a call of a method which is based on fields that are attacker controlled. So for example, the object input stream is a field which is attacker controlled. And then what we did is that we tried to answer several questions. Mainly, we answered the 6 research questions. For example, how these vulnerabilities are introduced in the code of both libraries that are used in applications, but also in Java class libraries of JVMs. And we discovered that there are a lot of actions that are innocent, but that they lead to vulnerabilities or to introduce vulnerabilities in libraries and in JCL. For example, changing the kind of a class from private to public makes the library vulnerable. We did the same for looking how these vulnerabilities were patched, and we found again a lot of actions, for example, adding allow deny lists, but also removing vulnerable classes that we found that they are vulnerable, etc. For example, here, I show to you one example of vulnerable version of JTK and patched version. Inside this, this version, we have the method read object, which is in a class which is called annotation invocation handler, and in which, in the context of a deserialization attack, this code will be executed, and we will arrive until the catch block, in which we have the return instruction. So in the context of deserialization attack, this return will return nothing to the caller, but the execution of the main program will continue. So the attack will continue. On another side, this vulnerability was patched by changing the catch block. So here we add, or the developers add an exception which will be thrown. So the whole execution, once this exception is thrown, the whole execution of the attack will stop. For the moment, we do not know if this was because they detect this deserialization vulnerability inside the code or for other goals, this correction. The third question that we were studying is about what are the vulnerable versions of libraries that were not declared in YSO-serial, because again, we were working using this YSO-serial tool, and we discovered that there are a lot of versions that are vulnerable, but they were not mentioned as vulnerable. For example, there is a library which is called Spring Beans, and for which we have detected that 140 versions are vulnerable. And for doing this, or for detecting these versions of vulnerable libraries, we have done more than 256 1,000 automatic experiments by varying the versions of JVM and the versions of libraries that are included in attacks. To conclude this work, so we did, of course, we were working on other research questions, but to conclude this work, we found that deserialization, even though it is so risky, developers are still using this concept or this mechanism without proper security vetting mechanisms. And we give some takeaway messages, like it is very important to prevent these attacks by, for example, inspecting these gadgets using fields that may be attacker controlled, for example, tainting these fields that may be controlled by the attacker, but also checking the calls of the read objects method, which is the starting point of these deserialization attacks. As a perspective of our work, we want to develop an algorithm to prevent this deserialization attack as early as possible. Thank you so much. And if you have questions, please do not hesitate.
Well, I have a short question. So can you hear me?
Yes.
Okay. So for the Java deserialization issue with that, so I'm not familiar with this area, but for the libraries you just mentioned, are they using the JDK's deserialization mechanism to do the deserialization, or they also have different separate deserialization mechanisms? Or if the vulnerability in the JDK is kind of like patched, then are those problems still exist if those libraries are using JDK for deserialization anyway?
So if I understood well your question, and in my point of view, these deserialization attacks or vulnerabilities are existing both in JDK or versions of JDK, but also in external libraries. So since the version, I think 17, Oracle was leading with this problem of deserialization, and they were trying to correct these let's say flaws in the JDK. But we found that they exist in JDK versions and also in external libraries that are used in applications, in Java applications.
Okay, I see. Yeah, thanks for the clarification. Okay.
Thank you.
So if there's no more questions, thanks for the presenter again, and we have the next presentation.
Thank you.
Hi, everyone. My name is Yuri. I'm going to be talking to you today about blind spots in Python and Java APIs and how they can result in vulnerable code. So this is work by myself and 4 psychologists. So we're really studying how developers and properties of developers affect their understanding of code. So those psychologists are Tia, Jesse, Alicia, and Natalie. All right, so what are blind spots? What are we talking about here? It'd be awesome if I could advance the slides. Nope, that's not it. Aha, magic. Okay, what are blind spots? So blind spots are actually super common in APIs. A blind spot, you know when you're driving and if you look in your mirror and you see what's behind you and you look, kind of turn your head and you see what's behind you, but you don't turn the right way, there can be a blind spot in your view, some part of the area behind you that you can't see. Well, the same thing can happen in code. There can be functions where using them seems straightforward and you seem to know what they're doing, but there's a blind spot. There's something weird that can happen in that function. So perhaps the best known blind spot is string copy. So string copy is a simple C function that takes a string and it copies it from source to destination. But if your source happens to be bigger than your destination, then it'll just write over whatever is at the end of your destination. So it's a buffer overflow problem. there was a study a few years ago that looked at why do developers make this mistake, because this has been known for something like 30 years, right? And if you Google string copy, this is the first thing that comes up, but people keep making this mistake. So why? So what developers said is that it's not straightforward that misusing string copy could lead to a very serious problem. It's part of a standard library, and so the developer assumes it's okay to use, and it's not called something like unsafe string copy. So if you go and you actually look at the specification for the thing, you'll see that there's a problem. But it's like a function you've used a million times. You don't go and look at the specification every time. It's easy to forget that something can go wrong, and so then you might use it and have this blind spot. So what do? We scoured vulnerability databases for things, for APIs that have blind spots, and so here's an example of a puzzle that we created using these APIs that have blind spots. It's a simple description of some code, and then there's a short piece of code, so here it's 8 lines, that uses some API that either has or doesn't have a blind spot. So this one is os.path.exists, which in Python happens to execute whatever argument you give it. So you can do a code injection attack this way. And then we ask 2 questions. The first one is just to make them think about the code, saying, what does this code do? Please describe it for us. And then the second was a multiple choice question that asks, what happens to this specific code when you use a specific input, which happens to exercise the blind spot if one exists? And then the developer will either understand what happens because it's a blind spot, or they won't. All right, great. So we created a bunch of these puzzles. In fact, we created 46 puzzles, 24 for Java and 22 for Python. And of the 24 Java ones, 16 had APIs with blind spots, and then 8 had APIs that don't have known blind spots, right? So they might, but they're not known ones. And the same thing for Python. And then we used this in a large user study. So the user study had 238 developers, and probably the biggest difference between this study and many user studies that you read about is that 161 of our developers were real developers, professionals working in companies. You know, we paid them real money to do this. And then a smaller number, 77, were students. And so we're able to compare how professionals act with respect to students with respect to these kinds of blind spots. All right, so the first question we asked is, what happens when you give people puzzles with blind spots and without blind spots? Do blind spots confuse people? They do. People are less likely to answer questions correctly when there's questions involve APIs with blind spots than without blind spots. So the black bar you see here is without blind spots, and the white bar you're seeing here is with a blind spot. And you can see that for both Java and for Python, you're more likely to answer questions incorrectly when there's a blind spot, right? This makes sense. But the effect is much stronger for Python. So in Java, people are actually more able to recognize blind spots and reason about them. All right, so an interesting kind of side effect is we said, well, maybe the Java puzzles were just more complex or something like that. Oh, sorry, the Python puzzles were more complex. So we looked at the complexity, which we measured as cyclomatic complexity, and we rated them as medium, low, high. And what we saw was super interesting. In Java, the more complex your code was, the more likely you were to be confused by the blind spot, right? You see the difference for the high complexity Java puzzles between the blind spot and the non-blind spot is much larger. So this makes sense. More complex, harder to answer questions. For Python, it was the opposite. For the more complex one, there was no statistically significant difference between having a blind spot and not having a blind spot. But for the simple ones, the low complexity ones, people made huge mistakes. All the time they made mistakes. So what's going on here? Well, we kind of have to do a little bit of speculation here, but we believe that in Python, for very simple puzzles, people had this kind of confidence, overconfidence. They thought, oh, this is simple, and they wouldn't think hard about it. But when the puzzles got more complex, they did think harder about it, and they recognized that there was a potential problem, whereas for Java, the opposite happened. So something about these languages is causing this kind of a problem. So we did see a cyclomatic complexity had an effect, but opposite for Java and Python. All right, the next thing we asked is whether developers considered puzzles to be more difficult, less clear, less familiar. Did those kinds of things affect stuff? And it turns out that no, they actually had absolutely no effect. So this is bad. This means that the developers were going blind, right? They did not know. It's not the case that they said, oh, something might be going wrong here, something is uncertain, I have to answer, so I'll pick a thing, but I'm not sure about my answer. That wasn't the case. They were equally confident when they were right as when they were wrong. So developers didn't have a sense that they're doing something wrong. All right, so that's bad. So then, remember working with a bunch of psychologists here, so we looked at things like what properties of the developer can actually affect things. And one of the things we looked at is long-term memory. So we tested long-term memory, short-term memory, all kinds of memory things. And not going too deep into this graph, but let me show you the result. If you had better long-term memory, turns out that you were statistically significantly more likely to recognize blind spots. But all kinds of other things, working memory, short-term memory, episodic memory, memory span, had absolutely no effect. So this suggests that if you have long-term memory and perhaps you've used this blind spot, you've run across it in the past, you might remember when you come across it again. But all other kinds of things that developers might think make them better developers actually had absolutely no effect. So only long-term memory is the only thing that helps. All right, so here's a really surprising one. Professional developers did no better than novices. So I told you we had students and we had professional developers, but we also asked them how many years of experience they had. So none of those things, whether they were professionals or students, how many years of experience they had, none of them had an effect of their ability to solve puzzles. So experts, you would think, they've been doing this for a while, they know what they're doing, they recognize these blind spots. No, they were actually overconfident and they were more likely to overlook blind spots, whereas novices were sort of didn't know as much, but they're more careful and looked at things and tried to think of them through. So experience doesn't help, which is kind of problematic. All right, so what are the main takeaways? So blind spots clearly reduce people's ability to reason about code, and long-term memory seems to help, but other things don't. And importantly, professional experience and education did not help. So what you need is you need tools that are able to detect that you're using an API and somehow, right at the moment you're using it, somehow tell you, here's some pitfalls you might fall into. And that kind of thing can help, because just things like education and experience are not going to save you from this kind of problem. So this paper that I just told you about is published in TOSM this past April, so a month ago. So if you'd like to learn more about this work, please go to read the paper in TOSM. Thank you very much.
Hi, thank you very much for the presentation. Great work. I have one question. When you recruited the professional developers, did you ask them like are they familiar with the blind spot like before, or like just you recruited them without any question actually?
So we didn't ask them if they're familiar with blind spots previously. We did ask them, of course, if they're familiar with Python, if they're familiar with Java, if they're familiar with APIs in general, but we did not cue them to the fact that there could be blind spots in code. That said, they each did 6 puzzles, and you quickly discover when we're asking you, what happens to string copy if your destination is this and your source is this, right? So they would get clues that we're looking at tricky corner cases with APIs fairly quickly, but we didn't explicitly tell them that.
Okay. Could it be that this might be the reason, like when you tested like the experience, the student doesn't have that much difference? It could be because of the developer you recruited doesn't have that much expertise in securing code, something like that?
We had a large number. We had 238 or whatever developers. So it's possible that some of them don't have experience in security, but these are developers working in companies full time. So I think it's a representative sample of what industry developers are like.
Okay, thank you very much.
Okay. Yes, you in the front.
Great talk. So, so when I see the Python and Java results, it's interesting and provocative. And I have maybe an alternate hypothesis that I'd like to hear you respond to. I think that Java developers and Python developers are qualitatively different in terms of their computer science skill and background. They're much more, there's much more breadth in Python developers and maybe not as much depth. What are your thoughts on this?
Yeah, so there's definitely something very different and interesting going on between the Python and the Java developers. We had done the Java study first and the Python study several years later. I don't know whether that could have affected things. I don't know. I mean, I gave this hypothesis. That's what's happening is that Java developers are on simple puzzles, they're thinking just as hard about them as the complex puzzles, which Python developers for some reason tend to see simple things and be like, oh, I know the answer, and rush through it without thinking hard. But for harder, more complex puzzles, they're thinking harder. But it's really just speculation. I'm not sure what's going on. There's definitely been a shift. When I grew up, when I got my SE education, everything was Java. I learned everything in Java. I teach, all my examples are in Java. But none of the students I teach today know Java. They're all Python, 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 right? So it could be sort of a generational difference, and it could be that people program differently now than they used to. But I'm just speculating about all of that. I don't know.
Great, thanks.
And there's actually, so in the paper, I showed you just a taste of the experiments. In the paper, there's lots more different personality traits and all kinds of things we measured about developers. So people who were more extroverted actually did better, and people who were more open did better with recognizing blind spots than people who are sort of more closed. So there's a bunch of other aspects, and whether those correlate with what language they tend to write in, maybe.
So you mentioned the analogy of blind spots to cars, but is there like a common definition of a blind spot, or was it something that was determined manually for each API?
So there is a common definition for a blind spot. It's a little vague. It's not definitive. It was defined by some of my collaborators, these folks and some others. So it's not like a super blind. But roughly speaking, it's anything in an API that might confuse you that's not immediately obvious, right? So a blind spot is actually the state that you might run into when you're using an API that has a vulnerability.
So not immediately obvious from like the documentation, or?
So often, if there's warnings in the documentation that here's a vulnerability that might happen, so the way we identify the blind spots is we look through vulnerability databases, right? And then we looked at, are some of these caused by APIs, and is it a confusion in the API that can cause it, or a misuse, right? So things like there's a return value that people often miss, like whether you open a new file, and if you fail to open a new file, it returns false, and you can just ignore that. That's a common blind spot. So people just keep going, assuming the file opened because they ignored the return value or something like that. So it's kind of a little bit of an art of identifying what is and what isn't a blind spot.
Okay, thanks.
Sure.
Hey, thank you for the talk. I was wondering, did you try to rank the APIs that had blind spots and try to see if there's an effect based on popularity? Maybe the very popular APIs, it's less likely that developers make mistakes?
I see. That's an interesting question. So popularity or sort of how well are APIs known? We didn't try to do this. We had 46 puzzles, which is not a huge set, but you need a set that's not too big so you can make generalizations. What was it? 32 of them had blind spots. Yeah, it's conceivable we could have done it with our data set and tried to somehow gauge popularity, just looked at open source code and seen how often these APIs are used. We didn't do that. That's an interesting thing to consider.
Okay, thanks.
We did ask people as they're answering the questions, are you familiar with these APIs? And there was no effect of familiarity. Thank you, everybody.